Okay, so let's now continue our exercises on normal subgroups. So in this next one, we have to prove that the intersection, we have two things to prove. The first is that the intersection of two normal subgroups in a group G is itself a normal subgroup, and then we have to extend this result to the intersection of any number of normal subgroups. So let's do the first part. Solution: let H and K be two normal subgroups of our group G. We need to prove that H intersection K is also a normal subgroup of G. Now we already know something. We already know that H intersection K is a subgroup of G. This we already know from properties of subgroups. Now to verify that this is normal, we take one element G in G and some element say H in H intersection K. We need to prove that the element G inverse HG also belongs to H intersection K. Then H being an element in the intersection belongs to both H and K. H belongs to H and H belongs to K. Now we use the fact that H and K are both normal subgroups of G. Since H and K are normal in G, we have this. G inverse HG in H and also G inverse HG in K. This implies that G inverse HG belongs to the intersection, hence the intersection is normal in G. So that is the first part. Then in the second part we have to prove that general one where any number of normal subgroups is involved, which is you can guess it's absolutely similar to this one, but still just for the sake of completion we are going to go through that also. Now, so here what we are given is that we have a non-empty set T, and for each element I in T, we have a normal subgroup Ni of our group G. So that means we are really here looking at a family of normal subgroups, an indexed family, that is this family, where the index set is T. And in order to avoid logical complications, it is assumed that T is non-empty. That means we have something, at least one normal subgroup is there. And logical complications I say because when you have the empty set T, then there are some complications that arise when you try to define this intersection, in that case when T is empty. Okay, so in this text, however, that has been avoided by assuming T to be non-empty when we define an intersection of sets where the sets are being labeled by the set T. So for us T is non-empty. Now we need to prove that this is a normal subgroup of G, just like all the Ni's are. Okay, so here also we already know that the intersection is a subgroup of G, that we know from the section that treats subgroups. Now, so we start accordingly. We already know that the intersection is a subgroup of G, and then the rest is similar. Let G be any element in G and H be any element in this intersection. So then H is going to be an element in each Ni. Then H belongs to Ni for each I belonging to T. Since now if you feel that you will get confused with this G and the previous G, that is the element G, and this H and the previous H, you can use some other symbols also. Although actually nothing is wrong in using the same symbol, because the job of that G and that H is over here. And anyway, these symbols represent arbitrary elements of these sets, so they can just be treated as variables. You can give any name to a variable. Just make sure that you do not use the, here also we are calling these elements G and H. So you do not actually use what we said over there about G and H. Okay. Then there will be a confusion. You just forget about what we did before. This is a new paragraph, so here we are treating new elements G and H, which have nothing to do with previous G and H. Anyway, so let's just now continue. Since each Ni is normal in G, G inverse HG belongs to Ni for each I belonging to our index set. But then by the definition of this intersection, G inverse HG will belong to this intersection because it belongs to each Ni, each set in the intersection. This implies G inverse HG belongs to our intersection. Thus, the intersection is normal in G. Now I must add here something about notations. When you write a solution like this, where you have to write things like this again and again at several places possibly, it's better to give it a single name. Say you call this capital N and then you just write N. That way it will be easier. And one more thing you can note here is that the result that we proved in the first paragraph, namely which has only two normal subgroups, is a consequence of this one. So you just take T as a set having only two elements, so that correspondingly you have only two normal subgroups. Then this is just a special case of this. So here the solution is over. Now let's see the next one. Let N1 a subgroup of N2. Here we have a sequence of subgroups. Let me digress a little and go back to this notation. Just now I said that sometimes it's convenient to call this something, right, like N or something, but that has a disadvantage also. That's because if you are writing clearly what it is, then you will never forget what it is. But sometimes if your solution or your proof, whatever you are writing, is really very long, it happens sometimes, then using just those names will confuse you. Okay, so you do whatever you want, whatever is convenient for you, but keep in mind you should not make any mistake. Okay, so now let's continue this. Let N1 be a subgroup of N2, which itself is a subgroup of N3, and it goes like that. And these are B, all of them are normal subgroups of G, of some group G. Show that this time their union is a normal subgroup of G. Now in the previous one, we just simply started off by saying that the intersection is a subgroup, which is something we already know. Here, however, we do not already know that the union is a subgroup, because normally when you deal with subgroups, union is not a subgroup, but you have special types of subgroups. Okay, it's not just a sequence of subgroups, but a nested sequence of subgroups, where each subgroup, each group is a subgroup of the next one. So here the situation is somewhat different than just having some subgroups. Okay, so we have to actually prove two things. We first of all need to prove that this is a subgroup of G, and then we have to prove its normality in G. So let's see the solution. But even before you prove that a subset of a group is a subgroup, never forget, you have to always make sure that the subset is non-empty. Sometimes this is overlooked, because if someone is going to prove that it's a subgroup, the first thing comes to our mind is the condition for a subgroup. The condition for a subset to be a subgroup. That only comes to our mind. We often forget the part which says that the subset needs to be non-empty. So never forget that. Here, however, that's easy to see. Clearly, we, however, mention it. Okay, we do not just simply go for the subgroup condition. Clearly, the union is non-empty. Why? Because the union contains all these subgroups inside of it as subsets, and each one, being a subgroup, is itself a non-empty subset, so the union is non-empty. Now let G and H be two elements in the union. We first of all need to prove that GH and G inverse both belong to the union, so that the union becomes a subgroup. Now we have chosen two elements in a union. Forget for a moment that we are looking at a union of subgroups. You just treat these things as sets. So G, for example, you just consider this first element G. G is an element in this union means what? G belongs to at least one Ni. G may belong to multiple Ni's, but we need at least one Ni. There is at least one set from among these Ni's in which G is an element. Like that, H also belongs to some Ni, maybe for a different type. So we write then G belongs to Ni and H belongs to, say, Nj. You cannot assume that H also belongs to Ni for the same I. That may not happen. For some positive integers I and j, because we have only positive integer indices. Things start from 1, 1, 2, 3 and so on. Assume without loss of generality that I is less than or equal to j. Now since I and j are two positive integers, one of them, either they are equal or one of them is less than the other. So we can assume this without losing any generality. Then looking at the subgroups, I mean the way they are related to one another, Ni is a subgroup of Nj, and so G being an element in Ni will automatically also be an element in Nj. Now G and H are both in Nj, and Nj is a subgroup of G. Since Nj is a subgroup of G, it's a normal subgroup, but we do not need the normality of Nj right now. We only need the fact that it is a subgroup. So because it's a subgroup of G and small h are elements in it, so GH and G inverse both belong to Nj. But Nj itself is of course a subset of the union because it's only one of the sets involved in the union. But this implies that GH and G inverse both belong to the union. Hence, the union is a subgroup. Okay, now we come to the question of it being normal in G. So we write like this. Next, because we have already chosen G, and although it does not matter, but still let's take some other symbols. Let U belong to G and let U belong to G. My handwriting is getting worse and worse day by day. U belong to G and phi belong to the union. Then since V belongs to the union, it belongs to one of the Ni's, then V belongs to say Nk for some positive integer k. Now we use the fact that Nk is a normal subgroup of G. Since Nk is normal in G, so U inverse V U belongs to NK. But just like before, just like this part, the previous one, since Nk is one of the Ni's, so now U inverse Vu will be an element in the union as well. What this implies, so that finally proves that the union is normal in G. Okay, so that completes the solution. Then let's see the next one. Let G be a group having exactly one subgroup. H of order n. Okay, so G has a subgroup H of order n, and that is the only subgroup of order n. Note one thing carefully, that G itself may not be a finite group. G may be infinite, but H is finite and H has order n, and it's the unique subgroup of order n. Show that H is normal in G. Okay, so already H is a subgroup that is given. We just need to prove the normality of H in G. And here we will need a result that we see in the theory part of this section, which is theorem 4.2. So we arbitrarily take an element G in G by theorem 4.2, the subset, which we write in the next line because we want to write what the subset is. G inverse H G, where the elements look like this: G inverse H G, and H is coming from H. This subset, I mean this is the subset and we denote the subset with this symbol. This subset by this theorem is a subgroup of G. Okay, so the theorem says that it's a subgroup of G, but additionally it's given that H is finite. So in that case, this subgroup has the same order as H. So we write also the order of this subgroup is the same as the order of H, which is n. But now you look at the hypothesis. The hypothesis says that H is the only subgroup of order n. But according to this theorem, this should also be a subgroup of order n. So the hypothesis forces us to conclude that this subgroup is actually equal to H. There is no other way, because we cannot have two different subgroups having the same order n. Since H is the only subgroup of G of order n, this forces us to conclude that G inverse Hg is equal to H. These two subsets are identical, but then G inverse Hg, which is how a general element in this set looks like, so that of course has to now belong to H for all H belonging to H. Now because we have also chosen small g to be any element in capital G, so actually we are looking at the statement which says that G inverse Hg belongs to H for every G in G and H in H. So that is just the condition for normality of H in G. Hence H is normal in G, and this completes the solution. So this means if we encounter in a group some subgroup which is the only subgroup of that order, a finite subgroup, then it must be normal. Okay, so it will be helpful if we remember this fact. It can be used. I mean, of course, every fact can be used to our advantage one way or another if the need arises, but this fact is quite simple and still the fact is strong at the same time. If you have a unique subgroup of a given order in a group, a unique finite subgroup of a given order, then it has to be normal in the group. And let me end the video here itself. I think 3 more exercises are there from this set of exercises. So we will complete this set of exercises in the next Lee update. And tomorrow, of course, we are going to continue our analysis. So see you tomorrow with analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.